a quick round of introductions for our panel, and then I think we'll just get straight into it. But obviously we have with us Noubar Afeyan, the founder and CEO of Flagship Pioneering and co-founder and board chairman of Moderna. We have Jason Kelly at the end here, the CEO of Ginkgo Bioworks, and Matt James, Chief Animal Officer of Colossal Biosciences and Executive Director of the Colossal Foundation. I think just to really start with, I think I want to pick up on something that Hugh said, which is, I think, getting into kind of the real potential for AI to transform scientific discovery. And I think this was something which was kind of a theme around the edges of Davos last year, but has really picked up momentum. And I think we've got three people here who, from very different perspectives, I think it'd be really interesting to understand where they think we are now and what the potential is for the future. So I think, Noubar, if I could come to you first. I mean, you've recently launched Pioneering Intelligence to harness AI across your own bioplatform ecosystem. I mean, how do you see AI fundamentally changing the questions you're going to be able to ask, the speed at which you can move to answer those questions and move to breakthroughs? And what are you already seeing between that convergence between AI and synthetic biology that might not have been possible even in the last few years?
Well, thanks for having me. So yeah, Flagship is an entity in Boston, Cambridge, Massachusetts, the New England, I guess, not kidding. You set me up for that. He knows that I'm on the executive board of MIT, so, anyway, we're competitive like they are. It's very good to see him at Imperial College, actually. I'm honored to be included in this discussion. So Flagship is basically in the business of conceiving and creating new companies based on science, technology that we develop in-house. And we've been doing this for now this is our 26th year. And across about 120 such companies, we've learned about how to improve the scientific discovery, technology, innovation process. And of course, we were in a position some 8 years ago to already see a kind of rumblings in what used to be the machine learning field, which we've been in for our entire 26 years. You have to realize in the life sciences, machine learning basically drove a lot of bioinformatics, and we've always had an excess of data we didn't know what to do with. And so this is not a new problem in our field. Mm-hmm. You know, the availability of data and then being vexed with what to do has been there. It's just that the models and the computers gotten better. So we jumped in and we started experimenting. One of the interesting things about disruptive kind of advances like this is that a huge number of people wait till it's validated, and then a few people purposefully don't wait till it's validated, because if they all wait, nobody's going to validate it. And so we decided that we should jump in and try to see what it's good for. And I would say 8 years into this journey, it's good for just about anything we've tried with it. And so it may not be good for summarizing, things without hallucinating. I don't know the things it's not good for in regular daily use, but boy, is it I would say unequivocally a prosthesis for human intelligence as it relates to science. And in that, I include creativity and imagination. I've been at so many panels during this week where people want to kind of argue whether human creativity is distinctly human, and of course it is by definition, but the fact that it's not extendable and amplifiable and augmentable is something that we don't see. Anyway, long story short, in proteins, we started a company called Generate Biomedicines 7 years ago. It has now a phase 3 asset that's computationally generated that is going after a particular important target in asthma, COPD, and 12 other programs behind it, several that have entered the clinic. In small molecules, in RNA, in DNA, distinct companies, in LMPs, data, massive amounts of data being generated to train models guiding decision-making, clinical development, patient selection. You can go to lots of different meetings, but we have this kind of interesting microcosm where we've tried it in a lot of things. So where are we on the journey? Kind of like prehistoric times in some regards because of where this is going to go. But the notion that there's a there, it's almost, so there's no question in my mind. And so I think we're excited because what it's doing is expanding the number of things we can do in parallel, which should ensure better outcomes if we are clever about how to parallelize, extending the number of things we could do in between each human intervention in the loop, which we can talk about later as well. Basically training systems on how to imagine like humans. It's not ideal, but it can certainly do a really bad job at it, which is very encouraging, by the way, because the rest is just kind of training. So yeah, I would say, and by the way, as it relates to academic activities, education, we have a very strong academic program within Flagship. We call it Flagship Academy, so we're incorporating it into that. We can basically take a bunch of memos and write a business school case without any intervention. One of the most known business school professors in innovation at Harvard Business School, Gary Pisano, left Harvard Business School, joined us a year ago after a 35-year career, and he's been actually playing around with AI to essentially encode tacit knowledge heuristics from 50, 60 companies. And so, pre-mortems, post-mortems, imagine automatically generating these types of things. So that's enough already. I left a lot for you guys.
Well, on that point, maybe coming to you next, Jason. I mean, be good to kind of understand from your business, how you're seeing AI changing biotech innovation.
Yeah, and so first, maybe, I'd echo your points that I think AI for science has been a big topic of this Davos in particular. Like, I just came from Satya Nadella did a AI for science hour breakfast this morning at the CEO of Microsoft, and I think it's because you're seeing demand from the public to ask, what is AI going to do that's going to impact my life? Right? Yeah, I know it's going to make us a little more efficient at work or whatever, make it easier to write emails, but like what's really going to matter? And I think a lot of the things that matter to people are things like medicines, and building things and the physical world and what science does. And so I do think this is a key topic for like the large tech companies and for AI. I think Nubar did a really nice job talking about how it's improving, like it's a prosthesis for our intellect, right? And it helps us in sort of the theory of developing science. I want to talk a little bit more about the kind of physical part of science. All right, so a lot of the work, if you go into a place like Imperial or MIT, you're going to see a lot of lab benches and a lot of people doing work to actually sort of query nature by running experiments at lab benches. And one of the things that we just announced at Ginkgo in December, so in the US, there's a new executive order from President Trump around the Genesis mission, which is to bring AI into science in the national labs in the United States. And Ginkgo was awarded a $47 million contract to build a 97 robot lab up at Pacific Northwest National Lab in December. And we also ribbon cut the first 18 robots with Department of Energy Secretary Wright. So I think this is a key initiative in the US, but what even is an autonomous lab? Like what's the idea? So I'll give you an analogy from what we've seen in transportation. So if I had sort of a y-axis here, and I put like how automated is it? Like level of automation. And then on the x-axis, I said, how flexible is it? So up in the top left here, you'd have little flexibility, high automation. In transportation, that's like a subway, right? You get on the subway, it's totally automated, but you better be going to one of the 5 stop or a tube, one of the 5 stops, okay? Down here on the bottom right, we have high flexibility, low automation. That's your car. And so since the Industrial Revolution, we basically had those two paradigms. We automated subway, we did that about 100 years ago, and we established cars about 100 years ago. And we've lived in that world where you're either doing everything manually and flexible or very inflexible and automated. And I think that's true across many areas of automation in our economy, all the way back to the loom and factories and everything. It's all low flexibility automation. All right, that's up until about 3, 4, 5 years ago, where you start to see Waymos all over the streets of San Francisco, because you now have a device up in the top right corner that offers you flexibility and automation. You get in the back seat, just like getting in a subway, but you tell it wherever you want to go. And we're going to rebuild our whole transportation system around that, because it's just fundamentally different than the automation we could do in the era of the Industrial Revolution. Does that make sense? And we even call it something different than automation. We call it autonomy, because it feels so crazy that you can get in a car and just tell it where to go, and it does it automatically, that we're like, I can't even call that automated. I call that autonomous. All right, so let me give you the analogy to science. Up here in the top left, low flexibility, high automation. In pharmaceuticals and places like that, we have robots in labs. We do high throughput screening. So pick a needle out of a haystack. I'm going to test a million molecules, run the same experiment a million times, try to find a great drug. Bottom right, high flexibility, low automation. Walk around the labs at Imperial. You will see a bunch of people like me during my PhD, sad PhD students hunched over lab benches, pipetting and working by hand at a bench that looks about like it did 100 years ago. And that's because, just like that car, that's been our only option for being flexible, which is what science needs. You've got to go interrogate nature and do whatever experiment you need to do that day, and you need that flexibility of the lab bench. So what's happened in the last couple years, thanks to advances in AI, just like with Waymo, we're getting to the top right corner, except it's not an autonomous car, it's an autonomous lab. And the scientist will be able to do this experiment, and the lab will just do it. And that, I believe, is going to change science, not because the models have to be so smart or think or be more creative than people, but that they will enable, just like the Waymo says, where does the person in the back seat want to go? The scientist will be able to say, I want to go there, and they'll get the experiment they want done. And so I think we're going to see a rebuild of not necessarily just the intellectual and the theory half of science, but the experimental half of science coming up. And we're excited to be part of that with the Genesis mission in the US, but I think there'll be similar efforts in the UK as well.
Yeah. And I think in a way that brings me to you, Matt. I mean, Colossal's got some really ambitious de-extinction goals, bringing back the woolly mammoth. You've obviously got a lot of work going on around, working with ancient DNA and multiplex gene editing. I mean, just picking up on what Jason said, I mean, what does that future look like for the sort of goals that you've got and the pace at which you're going to be able to achieve them?
Thanks. I think Colossal is an amazing example of sort of what AI is making capable. This idea of de-extinction has been, in the cultural zeitgeist for a long time. I mean, go back to Jurassic Park and everybody says, oh yeah, that's what a dumb idea. It's crazy. And now it's possible, right? Like,
Not a dumb idea. It's a great idea.
Yeah, I think, well, obviously, I mean, now that the way that we're doing it, it's possible, and that's because it is a convergence of amazing biotechnologies, but those biotechnologies are scaled and accelerated by using AI, right? Our ability, like Nubar mentioned, the computational side went from machine learning to AI. We can now make predictions about genotype to phenotype relationships, so that as we're going through a genome, a really beautiful genome that was assembled using AI is now being analyzed using AI, making predictions in silico, so that then we can go into the laboratory and more efficiently, more effectively make edits to a genome to have very predictable outcomes. That was never possible until the last 3, 4, 5 years, which is why Colossal spun up 4 years ago. I think where I see us going, and we've actually had Jason at the lab because we think, well, what's amazing about the work we're doing is that it's some of the most cutting edge stuff, but it is still relies on these 100-year-old techniques of having really sad, downtrodden PhDs hunched over a bench. How can we automate this? How can we get to a more of a, my CEO likes to talk about sort of a 3-shift cycle of science. How can we work 24 hours around the clock? Because the work we're doing is amazing, but the labs that we have to build are very expensive, and we're only using them for, half a day. Can we use them 24 hours a day? So I think that's where AI becomes this tool that makes science much more effective, but cost efficient, time efficient. It is allowing us to do amazing things like bring back species from extinction.
Great. I mean, I think moving on, I guess, this is all amazing potential. I think there's a lot of enthusiasm, there's a lot of hype we see at Imperial for the potential of AI to really transform that kind of scientific discovery and breakthrough. But I guess what would be interesting to hear, and I think perhaps coming to you, Nubar, given your range of portfolio of companies who are coming out with these new breakthroughs, how do we get them into the real world? How do we get that real world impact that kind of really does improve people's lives, whether it's their health, wealth, well-being? What are the barriers? What are the challenges? What do we need to do to keep pace outside the lab so that we can really feel the impact of these breakthroughs?
So maybe I'll just give a couple of examples and then I'll take this on. First, maybe I'll start with saying, the most popular topic to talk about in this Davos that I've seen is whether AI is hype. Mm-hmm. Second is just AI, but the AI is hype is even more popular, and I just find that perplexing because every new idea humans have had has been hope, and when it's not realized immediately, it's been called hype. Mm-hmm. And so the words just kind of differ by one letter. It's in our fields, that's a SNP. And it makes all the difference in the world. And so people kind of say, what is hype? And of course, it's true. Unrealized hope is hype. And if you're in this business, you've got to be willing not to kind of run away from that, but to say, yeah, but is the reward worth the effort? Yeah. And if it's to me, hype is when you're working on a useless problem and you have a lot of hope. But if you're working on something that, if it's true, could be transformative and across many different things like we're talking about. So I just want to point that out. Yeah. Having said that, so there's a couple of practical things that I can point to. We, many years ago, wanted to do this phenotype-genotype correlation in proteins. We wanted to be able to train models to be able to connect genotypes, the DNA sequence, to function of a protein without knowing anything about the protein's amino acid sequence or folding or any of the alpha fold stuff. We just said, you know what? Could we train with enough data function with DNA sequence? Now you might say, well, that's skipping a whole bunch of important molecular biology steps. And the answer is, last I checked, in nature, all that's passed on is DNA. Nature doesn't pass on codon tables, doesn't pass on Schrodinger's equation, doesn't pass on anything. It just passes on DNA. And voila, you get a protein with a function, not just a structure. And so we thought, well, if you have enough examples, this must be a data problem. And so we looked initially at the function of binding. And we trained models, initially transformer-based and diffusion-based and some bunch of hybrid models, LLMs thrown in, anything we could throw at it over 7 years. And what we did is we said, okay, here's a tough problem. Take a protein for which there's a known drug, for which you want to use the place on the target, not the antibody itself, but on the target that you want to tick a lever so that you have the effect you want. Why? Because if there's a known drug, you already know that the biology, once you do that act, can work. Now, why would you do that? Well, it's not to replace that with a me-too product, but you may want to make a significant advance to it. And you want to be completely free from any intellectual property around that original sequence, not by a little bit. So to do that, it's like a refactoring exercise. You basically ask a computer, you show enough instances of the bound state, and you just say, okay, suggest antibody sequences in the binding domain, and then you say co-optimize for the length of the protein's half-life in the body. And so we did computationally in a few months of work, we designed an antibody that looks nothing like, at all, sequence-wise, the protein that first taught us where to bind, binds in any measurement we've ever made identically, and instead of being used once a month, it's used once every 6 months. Now, you might say, well, that's very different than making a brand new antibody. Well, for that matter, it's actually harder than making a brand new antibody, because if you tried to do this through biological experimentation, it's a very hard task. Otherwise, people would make the same protein over and over again. So long story, what we learned is we've done that not once, but about 1,000 different times. We've made different antibodies for different targets to prove this capability. We've now made proteins that are enzymes, de novo, and many other things. So I just will point that out as one example. The other thing I'll say, just to extend Jason's description, is his company, interestingly, is enabling the autonomization, let's say, or further automation of labs, and particularly, obviously, integrating steps. We've been interested for multiple years. For about 3 years, we've had an active effort in a company called Lila to actually take the scientific discovery process and see if we could make the entire thing autonomous. Right. And I'll add to the picture, because everything in science is additive, I'll add to the picture that it's one thing to set a Waymo out in roads that you have some information out. It's another thing to set it out in a place where there are no roads and essentially nobody's ever seen before. Yeah. And science, at its cutting edge, is about the unknown. It's not about the known. So when you want to navigate the unknown, that's where human hypothesis generation, intuition, absorbing the totality of what's known to come up with what could be alternative descriptions of what's next, all of that we also have trained using generative AI. So we have capabilities now to take just about any aspect of science, and we've done this in chemistry, in biology, material science, all aspects of biology, biochemistry. And you can basically take everything that's ever been published, every piece of data that's ever been in the supplement section of every paper that's been published, the raw data that has to be disclosed, and essentially trained to come up with hypotheses that are significant projections over the present state of the art. And we're kind of using this to do the cognitive part of science and the autonomous experimentation part, both within the same system. And what's interesting is that allows us to generate data not to solve a problem, but to train models that go way beyond the data that's existing publicly. So it's a company called Lila Sciences. We're early in that journey, but we've been doing this for 3 years. It's about a 250-person effort. And we're very excited by the beginnings of what we're seeing, which is a very different capability than what we've seen human scientific enterprise do so far.
Great. I mean, maybe Jason, coming to you. I mean, your company works with government and other corporates globally. So I think maybe two questions. I mean, one is picking up on Nubar's point about this kind of, is AI just hype? It'd be interesting to see kind of what sort of reaction you're getting when you're out in industry and with governments talking about the potential of AI. And also, I guess, kind of what barriers there are to then scaling the impact of some of the work that you're doing in biosecurity and biotech and in that kind of automation space.
Yeah, I will touch. I'll touch on that. I will say it's hard to sit next to Matt on the application thing because nothing's going to be cooler than Jurassic Park. But and I'm the generation. Anyone my age in biotech, I was 13 when Jurassic Park came out. We're all in the industry because of Jurassic Park. So let's just be clear. Look, yeah, we're seeing like our customers for this are folks like the national labs, government labs, and then pharmaceutical companies, diagnostics companies, people that run a lot of lab work. And so I do think. We are seeing uptake. You're seeing a lot of people trying to understand how to put AI into their business. It's like anything else. I think the biggest like business model challenge for this whole space, I think if you look across any technology that's applied to improving research, is does the industry buy like horizontal tools in that area? And so it's very rare to actually see that. So if you look at the pharmaceutical company, the majority of the tooling is all vertical, right? They have all their own stuff, right? You look at a chemical company, same thing. There's a couple exceptions. The tech companies, everybody writing software runs horizontal. They all use cloud. They all use GitLab or whatever. And also in chips. Semiconductors, you outsource to Cadence or Synopsys to do your CAD tools and all these types of things. And in fact, I personally think that's why those industries move so quick. Yeah. Is they figured out how to have players provide tools to the app developers and not just have every app developer make their own tools. Yeah. And I do think we should. This is a chance to bring that model into a lot of these other industries, which I think could really help speed drug development. So that's what I'll say. I will give you though one other sort of application. Well, and I should mention also on the biosecurity side, let's just say the U.S. and the rest of the world remains very exposed to pandemics. I do think, and Newbar's flagship has some great companies here too, this opportunity to say, if I look at what's happening, if I look at sort of genomic data, whether it's in wastewater or in the air in this room or anything else, if you run that through an AI model, you should be able to start to be predictive about, is there something bad in there without having a bunch of scientists checking by hand. So I think there's real opportunities for like safety here as well. One vision point for you. Okay. So my personal view is if we can solve the autonomous labs technological problem, fast forward 5 years, and I don't think there'll be any lab benches.
Right.
All right. My view is that the lab bench has been the principal barrier to entry for everyday people to get involved in science. And that seems crazy, right? Like, I gotta get a PhD, you gotta learn all this stuff, science is so hard, we couldn't have millions of scientists, that's crazy, right? But if you go back to, say, 1960, in the computer industry, if you wanted to be a software engineer, boy, I hoped you worked at MIT or IBM, right? And you had access to mainframes. You also better be an electrical engineer because you got to know how to like connect wires and do all this complicated stuff. And what we did over the next 70 years was basically abstract all that complexity out of software engineering so that my 11-year-old can program computers now.
Yeah.
Okay, so why couldn't we do that in science? Why couldn't we have just the general public being able to say, hey, I've got this question about my health. I got this question about this plant in my garden, whatever it might be, and being able to operate as scientists with these tools as we virtualize them, as we virtualize the lab bench, just like we have done with computers over the last 70 years. And I think there's an opportunity for that. And so I'm excited more about, could we enable lots of people to develop apps than actually, frankly, the relatively small number of apps today that are plugged into science.
Yeah. And Matt, to come to you, and I think picking up on what Jason said, I think the area you're working in is both incredibly exciting, but in a way it's illustrative of an area where people may also be quite concerned. It's both an exciting and perhaps a slightly frightening. Perhaps not in this room, but more broadly. So, I mean, what do you see as the sort of policy frameworks, the regulatory frameworks that could be put in place or should be put in place that would still enable the work that you need to be doing and you want to be doing, but are going to provide that kind of sense of this is kind of responsible application and adoption of AI technology?
Yeah, I really enjoy AI because it's not only an amazing tool that we utilize, but it's also a great allegory for de-extinction technologies. We can look at people and say, well, remember 20 years ago, or even go back 40 years, there's a movie Terminator, and everybody was afraid of AI, and it was going to kill us all. And then people go, well, you're starting a de-extinction company. Did you ever watch Jurassic Park? It's like, well, you're not afraid of AI. It's on your phone now. It's a tool that you already use. Yeah. You're writing emails using it. So, sort of to Jason's point, it becomes normalized. It becomes much more accessible. same way that I hope de-extinction will and is doing so. So we're really invested in working with regulators and stakeholders because our technologies are scary. How we use AI is very different. We're getting to a point where we can begin to create foundational models with all this amazing data that we've created that can really begin to help reverse engineer life, sort of, like Nubar was explaining with antibodies. We can begin to look at organisms that way, and instead of needing a DNA sequence from an animal, we could begin to even potentially just plug in specific phenotypes that we want to see, and AI can tell us what DNA sequence might be most associated with those phenotypes. So that's a scary technology that needs a lot of regulation, needs a lot of boundaries, and so that's one of the things that we're focused on, is trying to be a subject matter expert as we go and engage with regulators in the U.S. and internationally to try to say, here's the art of the possible, here's why we think we need a pathway to success, but here's also some guardrails that would be really important. And I think, AI has sort of unlocked this incredible vast scale of the art of the possible. That is what's really scary, and where we see the most effect in terms of when people are asking us, should you do this thing? And so we want to begin to show responsible use of AI as a tool of de-extinction, and then as a force of nature restoration. And I think what's really neat, and sort of to answer one of the earlier questions, is the way that we can sort of look outside of our lab and demonstrate AI is not just a tool for the everyday person that is like an LLM.
Yep.
Really show them where AI is an empowering tool, is in nature restoration.
Yep.
Using AI for de-extinction is one piece of the puzzle. We begin to put animals back in the wild to restore ecosystem function. How do you measure the lost function, and how do you measure the effect of the restored function? Is with massive data sets and multimodal sensors that are collecting all this data and beginning to give us real-time information for nature, for how we are creating improvements to humanity through improving nature. So some of the biosecurity concerns that come up are also, I think, need to be focused on the nature side. Yeah. Right? What are the things that we're losing in nature that are having these massive impacts on our things like health or water security, food sovereignty, things like that? And so, we're deploying tools in the lab with AI, but now we're beginning to deploy AI tools in the field as well. How can we track wildlife? How can we detect changes in environment? Can we almost create a canary in the coal mine sensor that's out in the environment and begins to make predictions for where ecosystem degradation is happening, and we need to quickly act? The conservation space is highly resource limited, so the best thing we could do is have this robust data set and really strong predictions to say these are the hot spots that need attention and investment. And so we're beginning to build those tools today at not just at Colossal, but at a nonprofit foundation.
Great. I think this might be a good moment to see if we have any questions from the audience. I've got a few more to come from me, but if we've got one from Hugh.
Just for avoidance of doubt, I should say that Imperial PhD students are not downtrodden. Just want to put that on the record. I just love the binding story. And just an extension of that, throughout history, so many of the drugs in common use, from aspirin, maybe all the way through to GLP-1 agonists, have seemed to do more than they were originally predicted to do, and mechanisms of action turned out to be quite different to what maybe they were originally predicted. Have you or any of your companies take that almost retrograde look, taking some of the iconic drugs and then moving backwards through the chain to identify new sites in disease pathogenesis and potentially identify new targets?
Yes. There's actually a company that we have, a small thing, that's been doing that for a while with just amazing success and somewhat resulting disappointment, which is kind of a curious thing. It makes your point. So we said, why don't we pick all the drugs for which there's no accepted known target that are approved and go find the target. And we looked at multiple so far. All of them bind to a whole bunch of different things, and their action is pleiotropic. You cannot isolate a single target, because we've done the work to actually do that. Most people thought the target exists, but they can't find it. When you find the target, you can't find it because it's not one target, which actually allows me to make a different point, which is, humans, biology is always, in any kind of field of science, is a function of what you know already at the time you're doing it and the tools you have available. So given that, I think that this industry, pharmaceutical industry, has gone historically from kind of like searching in soil for chemicals and antibiotics, it's alike coming from different life forms, to at some point when DNA structure was revealed and things wanted to become molecular, I think we overshot massively and basically came up with this human paradigm. You know, humans have memes. Basically, the dominant meme is target-based drug discovery. The industry loved this. In other words, if only there was a target, our job would get easier. And so therefore, there must be a target. We just have to go find it. And so we have superimposed on nature a specificity of a single switch. Right? In this room, I could probably turn the lights off with one switch. That's because a human designed the room and left a switch for me. Who designed these living systems and left a switch for us? That whole target-based paradigm is a way to convince both the scientific community, frankly, and the regulators that we know what we're doing. Mm-hmm. The reality is that what AI is showing us, and I just say this to you both to inspire and to depress you, is that with AI models that have hundreds of billions of parameters, such as these language models, but now applied to science, the language of science, and the chemical, biological language of science. What we're beginning to do is to remotely match nature's complexity in any given system with these model complexities, leaving behind humans in this dynamic where they're surrounded by nature's intelligence and machine intelligence with an odd place. Because we are the ones who have agency, at least for now, we control the resources and the intentionality, and we don't understand either what the machines are doing or what nature's doing. But they may well emulate each other, at least computers can emulate more and more nature's complexity. So we'll have a choice to make, and I really think this is going to be one of the interesting bifurcations in this industry. I think a lot of people, including the pharma industry, will insist that anything we don't understand, we should discard and favor things that we do understand. And then the AI world will come along and say, actually, the only things that we're working on are the things we can't understand because you have no other way as a human to work on them. And guess what? One way of understanding all the diseases for which we have no solution, or we have no early detection markers, or we have no ways to track the effect of drugs, is by studying the complexity in its native form, not in a reduced form in a test tube with graduate students who are happy or sad, but basically an abstraction. We're, as humans, really good at simplifying problems that are complex by picking one little piece of it, reproducing it, and saying, see what I could do reproducibly, let me publish. That's kind of led to a whole gigantic tens of billions of dollars industry. I think that's about to change. So we're entering kind of this interesting world. In another panel setting, I kind of throw out this notion. As you may know, in the field of biotechnology, the tech AI-driven crowd, who basically just wants this to be a computational problem only, has invented the word tech bio. And so they go around basically saying, no, it turns out that the biotech people had it wrong, and it's really all about tech bio. And I would say, just to show my age, I've been doing this for 39 years. I actually think the ultimate solution is going to end up being biotech bio. We're going to have to start with bio, and that is all the data that's available that we can get from the system. That is, tech is just an enabler of that. Use the tech to be able to actually create some semblance of a model or many models around it, and then end up back in the bio world. And so if you don't have the bio in the beginning and you don't have the bio at the end, I don't think you're going to have a lasting role. This is not about a tech stack. Yeah. There's going to be a bio and a tech stack together. So I'm expanding kind of your question, but that's what I see happening.
We've heard a lot about kind of some really incredible things that are going on in your different companies and in different labs. But I think perhaps I speak for this audience, it's always good when I have a group of people like this to say, what's next? What do you think is coming down the road in the next 3 to 5 years that's exciting you, that's giving you hope, not hype? Start with you.
I think what excites me the most is sort of in that same vein, the early detection nature systems that we're creating now to really understand what are the natural disasters that are coming. And I'm not talking about hurricanes and tornadoes and fires. What I'm talking about are what are the ecological collapses that are occurring in nature right now that have gone undocumented for generations. Are we able to now to make these predictive measures that it begin to allow early detection, early action to create an opportunity to avoid real disaster that we can't come back from? We talk about de-extinction as this idea that we can reverse extinction. right? And we all know that that's really hard to do, and it's a really complicated topic, and we could debate all the semantics of de-extinction. But what we can all agree on, and even as a de-extinction leader, what we can agree on is it's better if it never went away to begin with. AI has given us the ability to make those early detections, those early predictions, begin to make more efficient early action to prevent loss.
Great. Jason?
Freeing the sad MIT grad students from the lab bench. I am excited. I am generally excited about reducing the barriers to science. I think you will see that over the next 3 years. You'll actually see it first with the models in things like math and coding, where the barriers are falling left and right. Like you see people on Twitter posting math proofs and things like that. That's super exciting, right? If we can bring that into more areas of science in the next 3 years, I think it'll change the world.
Great. And Nuba, final word?
Of all sorts of exciting things that say preemption of disease will be even a lower hanging fruit than finding external threats, because these threats are inside our bodies. And we've basically waited till these threats get really advanced and manifest in a incurable disease, and then we'll do something about it and wonder why it costs us so much to do that, let alone take care of the people we can't really do anything about. So I think that with data, trained models based on just population data, followed by more specific hypothesis-driven ways to create models, we are being able to detect your likelihood of getting a diagnosis, let's say with Parkinson's, let's say with NASH or MASH, all sorts of diseases we're showing 6 months, 3 months, 9 months earlier. Obviously, you'd like 10 years earlier with Alzheimer's, but many months earlier, which means that you can now intervene before even the disease is diagnosable. Now, of course, as soon as you could do that, the medical field will declare the disease, whatever you said was the pre-disease, which, by the way, is okay from a reimbursement standpoint. But in the meantime, we have to work on preemption of disease, which is detecting, delaying, stalling, things that lead to disease. I think as humans, we have, one last point I'll make is, we call healthcare, it's the best marketing term ever invented, because it's actually sick care. And other people have made this point, we've been making this point for 10 years. And so if a marketeer wanted to disguise sick care, they would call it healthcare. And you know this, by the way, because you only get any of it when you're sick. And so how is this healthcare? Now, people can talk about longevity and living well and all that all they want. They don't consider that healthcare. They consider that something else. When healthcare actually becomes healthcare, we should be spending 10, 20, 30% of our healthcare costs upstream of disease. Today, we spend 2 to 3%. Yeah. And so I would say one of the more kind of futuristic things would be if government said, you know what, take 5% of the money, 10% of the money, and just you have to spend it upstream of disease. What would that society look like? With AI, completely different.
Yeah. Well, I think that is a really optimistic note to end on. So if everyone would just thank the panel for what I think was a really interesting discussion. Thanks very much.